not find a way to explain what they were seeing without seriously considering the possibility that something once was alive there. Not proof, not confirmation, but the closest thing to it that anyone has ever found. In the story of how that rock was discovered, what it might mean, and why scientists are being so carefully, almost painfully cautious about calling it what everyone wants to call it, is one of the strangest and most consequential detective stories in the history of space exploration. To understand why this single rock matters so much, you first have to understand how long humanity has been staring at Mars and wondering the exact same thing. For thousands of years, that reddish point of light moving strangely against the fixed stars' unsettled ancient sky, Babylonians associated it with Nergal, god of plague and destruction. The Romans named it directly after Mars, their god of war, because of its blood-red color in the night sky. It was a planet defined by fear and myth long before it was defined by data. That began to change in the 17th century, when astronomers with early telescopes started sketching polar ice caps and seasonal changes in its surface color, features that seemed almost eerily similar to Earth. By the late 1800s, an Italian astronomer named Giovanni Schiaparelli described faint linear features on the Martian surface he called canali channels, and an American astronomer named Percival Lowell ran with the idea, building an entire observatory in Arizona dedicated to mapping what he was convinced was a network of irrigation canals, built by a dying alien civilization desperately funneling water from the polar ice caps to save their world. Lowell was wrong. There were no canals. But the myth he created was so powerful it inspired H.G. Wells to write The War of the Worlds and shaped an entire century of public. Real science finally caught up with the myth in 1965, when NASA's Mariner for spacecraft became the first probe to successfully fly past Mars and photograph its surface up close. The pictures it sent back were devastating to the romantic vision Lowell had built. No canals, no cities, just a cratered, barren, apparently lifeless world, closer in appearance to the moon than to Earth. For a moment, it seemed the question was answered, and the answer was no. But scientists weren't satisfied with a handful of grainy photographs. And in 1976, NASA landed 2 spacecraft directly on the Martian surface, Viking 1 and Viking 2 carrying, among other things, a set of biology experiments specifically designed to test Martian soil for signs of living organisms. One of those experiments, the labeled release experiment, produced a result that, if it had come from a soil sample on Earth, would have been interpreted immediately as evidence of microbial metabolism. Gas was released from the soil in a pattern eerily consistent with biological activity. For a brief, electrifying moment, some scientists on the mission team believed they had found life on another planet. Then came the doubt. Other Viking instruments failed to detect any organic molecules in the soil at all, which seemed almost impossible if living organisms were present. And the scientific consensus that formed over the following decades was that the reaction was most likely produced by unusual, highly reactive chemistry in the Martian soil, rather than biology. The question wasn't answered. It was just buried under uncertainty for 20 more years. Then, in 1996, it exploded back into public consciousness in a way nobody expected, when a team of NASA scientists led by David McKay announced they had found what appeared to be microscopic fossils of ancient bacteria inside a meteorite, a chunk of Martian rock called ALH84001, that had been blasted off the surface of Mars by an ancient impact and had eventually landed in Antarctica, where it was discovered in 1984. The announcement made front-page news around the world. And then, over the following years, the scientific community picked the claim apart piece by piece. The microscopic structures were far smaller than any known bacteria on Earth. The organic compounds found alongside them could plausibly have formed without any biological process at all. Most scientists ultimately concluded the meteorite was not convincing evidence of Martian life. It became a landmark lesson in the field of astrobiology. That hard-won caution is exactly why, decades later, NASA's newest and most sophisticated rover found something even more compelling than anything Viking or that meteorite had produced. The scientists behind it refused to rush to a headline. The rover is called Perseverance, and it landed inside a Martian crater named Jezero on February 18, 2021. After a descent so complex and so risky that mission engineers nicknamed its final phase the 7 Minutes of Terror, sequence involving a supersonic parachute, a rocket-powered descent stage, and a device called the Sky Crane that lowered the rover to the surface on cables before flying off to crash safely at a distance. All of it happening automatically, with no possibility of human intervention because a radio signal from Earth takes too long to arrive to control a landing in real time. Jezero Crater was chosen deliberately, out of dozens of candidate sites, because billions of years ago, it wasn't a crater at all, it was a lake. Orbital imagery revealed the unmistakable fan-shaped delta of an ancient rive that once flowed into a body of standing water roughly the size of Lake Tahoe, and on Earth, deltas like this are extraordinary preservers of biological evidence. It's because fine sediments settle slowly and can entomb organic material for eons. This was one of the most promising places in the solar system to look for its fingerprints. For 3 years, Perseverance explored the crater floor, drilling into dozens of rock targets, sealing samples into pristine titanium tubes designed to be picked up by a future mission and flown back to Earth. And then, July of 2024, the rover drove out of the crater itself and into a winding river valley called Neretva Vallis, which had once carried water into the ancient lake. Along the edges of that valley, in a set of rocky outcrops, geologists named the Bright Angel Formation. The rover's camera spotted something that immediately caught the science team's attention: an arrowhead-shaped rock.
Roughly 3 feet across, marked with strange,
small dark flecks the team nicknamed poppy seeds, and larger, pale, ring-shaped markings they called leopard spots. They named the rock Shayeva Falls, after a waterfall in the Grand Canyon. It looked unusual even to the naked eye. What it contained turned out to be far stranger. Perseverance carries 2 extraordinarily sensitive instruments built specifically for this kind of investigation. PIX, which stands for Planetary Instrument for X-ray Lithochemistry, and Sherlock. When PIX mapped the chemistry of those spots at extremely high resolution, it found something unexpected: 2 distinct iron-rich minerals arranged in a very specific layered pattern. In the black poppy seed flecks, and along the outer rims of the larger spots, the instrument detected vivianite, a mineral made of hydrated iron phosphate. In the interior of the spots themselves, it detected greigite, an iron sulfide mineral. The arrangement wasn't random, formed what geologists call reaction fronts, precise boundaries marking where one chemical environment gave way to another, as if some process had moved through the rock, stripping the reddish, oxidized iron out of its core and depositing these 2 new minerals in its place, layer by layer, like rings in a tree trunk, record a history of growth. And here is why that mattered so much to the scientists studying it on Earth. This exact combination, vivianite and greigite, forming together through the reduction of iron in organic-rich sediment, is a chemical signature strongly associated with microbial activity. Vivianite is frequently found in peat bogs, lake sediments, and the decomposing remains of organic matter. Certain microorganisms actively produce greigite as part of their metabolism, using redox reactions, the transfer of electrons between molecules to extract energy from their environment in much the same way your own cells extract energy from the food you eat, releasing byproducts as they go. If living microbes had once existed in the mud, that would eventually become Shayeva Falls, feeding on the organic carbon trapped within it. This is close to exactly what the chemical evidence left behind might be expected to look like. For the geologist leading the investigation, Joel Hurwitz of Stony Brook University, the moment the team began seriously considering that a biological explanation might genuinely be the best fit for the data was, by his own account, difficult to process. He would later describe lying awake that night, turning the implications over in his mind, aware of exactly how significant and exactly how easy to get wrong a claim like this could be, because the scientists knew better than anyone. The cautionary history stretching back through the Viking mission and the ALH 84001 meteorite, they knew that vivianite and greigite can, under the right conditions, also form through entirely non-biological chemistry through simple, ordinary interactions between minerals, water, and trace organic material, no living organism required at all. There is no instrument on Perseverance capable of That caution exists inside a much larger ongoing search that stretches far beyond a single rock and a single crater. Mars is not the only place in the solar system where scientists suspect the ingredients for life might exist. Beneath the icy crust of Jupiter's moon Europa and Saturn's small moon Enceladus, spacecraft have detected strong evidence of vast liquid water oceans kept warm not by sunlight, which barely reaches those distant worlds, but by the immense gravitational flexing of their parent planets, a process that generates internal heat the same way repeatedly bending a piece of metal warms it in your hands. Enceladus is especially tantalizing because NASA's Cassini spacecraft flew directly through plumes of water vapor erupting from cracks near its south pole and detected organic molecules and hydrogen gas, a potential energy source for microbial life, venting directly into space, essentially sampling an alien ocean without ever having to land or drill. Neither Europa nor Enceladus has produced anything as specific or as scrutinized as the Shayeva Falls signature.
8 put together.
These worlds have transformed the search for life beyond Earth from a question about one planet into a question about an entire category of worlds. See moons with hidden oceans that may be far more common throughout the universe than anyone assumed even 20 years ago. Mars remains the most accessible of these candidates. It's the only one where a wheeled rover has ever driven across the surface and drilled directly into ancient rock, which is exactly why its evidence, however carefully hedged, carries so much weight. There's a deeper, more uncomfortable question sitting underneath all of this careful science. One that scientists rarely say out loud in press conferences, but that shapes every decision about how this research moves forward. What happens to human civilization the moment this question is finally, unambiguously answered? For centuries, religious traditions, philosophical frameworks, and cultural identities across the planet have been built, at least in part, on the assumption that life on Earth is either singular or the deliberate product of forces unique to this world. Confirmed evidence of independent life on another planet. Even simple ancient microbes long extinct would not simply be a scientific curiosity. It would force a re-examination of some of humanity's oldest and most deeply held beliefs about our own significance in the universe. Some scientists and ethicists have spent years quietly studying how such an announcement should even be communicated to the public, precisely because they understand that unlike most scientific discoveries, this one would not stay confined to academic journals. That is part of why NASA's scientists have been so relentlessly careful with their language around Shayeva Falls, not because they doubt perhaps better than anyone the weight of what a genuine confirmation would ultimately mean. For now, that verdict waits on Earth. Inside laboratories not yet built to receive a sample not yet delivered, from a mission not yet fully funded, examining a rock that is, at this very moment, sitting silently inside a rover parked on the floor of a crater that used to be a lake, on a planet that used to look a lot more like our own. It is entirely possible that the single greatest scientific discovery in human history, definitive evidence that life has existed somewhere beyond Earth, already exists, sealed inside a titanium tube, sitting on the Martian surface, waiting for humanity to find a way to bring it home.
Oh.
We have already done the hardest part of finding it. What remains is the harder, slower, more expensive work of proving it, a process that may take years, and that may ultimately disappoint as easily as it may astonish. But even in that uncertainty, something has already changed. For most of human history, the question of whether we are alone in the universe was philosophy, myth, and speculation. Babylonian gods, Roman legends, Percival Lowell's, fictional canals, decades of ambiguous chemistry, X-prime, NTS, that were argued over and ultimately dismissed. Today, for the first time, that question is sitting inside a specific physical object, with a name and a location and a peer-reviewed scientific paper attached to it, awaiting a specific, achievable, technological effort to finally answer it. We are not chasing a myth anymore. We are chasing a rock. And somewhere in the mineral rings of that rock, 3.5 billion years old, formed in the mud of a river that stopped flowing long before anything resembling a human being ever existed to wonder about it, might be the answer to the oldest question our species has ever asked. Are we, in fact, the only ones who were ever here?